Welcome to Week 2 of Systems at Scale 2021 Spring Edition. My name is François and I am an engineering director at Facebook. This week we will focus on the topic of storage. First, we will have Dan and Chidam who will cover some of the video storage optimization we implement at Facebook. In the second part of this session, Sazala Reddy from VMware will dive into the design of a new multi-purpose cloud file system. Enjoy the talks and see you right after, live for the Q&A.
Hello, I am Chidambaram and I'm a software engineer here at Facebook, based in Seattle. I work on infrastructure for storing, processing, and delivering videos. Working from home during this pandemic, I got time to get back to an old hobby of mine, pencil sketching. Sketches usually start off as a rough outline. Then we add features and refine them iteratively until it looks just right. Here at Facebook, we took a similar approach to solve a video storage problem. When we started off, videos were just stored like any other blob. But over time, we discovered that we could be storing them much more efficiently if we could use some of the properties of the videos. We call this approach semantic replication. Today, my colleague Dan and I will be talking to you guys about how we went about doing this and what changes were required to make this work. Facebook has its own blob storage system called Everstore. It stores trillions of blobs and exabytes of data. Videos account for majority of the bytes stored and are also the fastest growing content. To keep up with this growth, we realized we need to optimize how we store these videos. So, what are the key insights about videos that can help us store them more efficiently? Typically, videos in general are larger in size compared to other content types, let's say photos. Also, videos can vary quite a bit in size. For example, Instagram stories are short and smaller in size compared to gaming videos, which can be hours long and their size can run into multiple gigabytes. Videos can be watched over networks that have varying bandwidth, and they can also be played on a variety of devices and players. To support this, videos are typically re-encoded to produce multiple resolutions, or encodings as we'll refer to them from here on. It is possible for videos to be watched as they are being uploaded. Live videos are a good example of this. In such cases, we need streaming access or access to bytes as they are being written. Lastly, videos have a very interesting property called the temporal access pattern. Most videos are watched closer to upload time, and as time goes on, the chances of a video being watched reduces significantly. Let's consider this video. This one has been re-encoded into multiple resolutions, a high resolution, a medium resolution, and a low resolution copy. And all of these are stored in Everstore as their own objects. The interesting observation here is that all three of them represent the same content. That is, humans viewing any of these resolutions will derive the same meaning even though they can tell the difference in visual quality. In other words, these encodings are semantically equivalent. We will refer to such copies as semantic replicas. Also, since video encodings can be large, they are split and stored as multiple chunks. Each chunk is a blob from the storage system point of view, and each of these blobs is actually stored with two physical copies for disaster tolerance and to improve availability. These copies are bitwise identical, and we will refer to these as physical replicas as opposed to semantic replicas that we discussed earlier. So this is all great, but how do we use these insights to optimize storage? The key idea is to treat these semantic replicas as interchangeable copies of the content. We can see that in the default layout as shown here, there are two semantic replicas and each of them has two physical replicas. If we served either the high resolution or the low resolution encoding, the player has two physical copies to read from. But what if we stored just one physical replica for each semantic replica and let the player switch between these semantic replicas? We still have two copies of the content, but we have reduced the storage requirement by 50%. This sounds too good to be true, right? What's the catch here? Let's say each physical replica is present in a distinct failure domain for disaster tolerance. Failure domains are usually regions, which are just a collection of data centers in the same geographic area. Under normal operating circumstances, all of these replicas are accessible. But in the rare case of natural disasters or other catastrophic events, a region could become unavailable. Let's say in this case, region C goes down. With the default storage layout, there is still one high quality resolution encoding that can be served to players. But with the compact storage scheme, we only have the low resolution encoding now until region C becomes available again. This can cause degraded experience since we can no longer show high resolution content. Also, reduced physical replication implies higher chance of read failures, which can cause player stalls. So, can we somehow mitigate this issue while also saving on physical storage? Turns out it is possible if we consider one of the key insights from earlier, temporal access pattern. Videos get watched very little after a few days of upload, and in this state, we call them cold videos. Here at Facebook, we built a mechanism that tracks when videos become cold, and we target only those videos for semantic replication. This approach has two advantages. First of all, since these videos are cold, the chance of these videos being watched again is very low, thus addressing the experience degradation concern. Also, since videos become cold over time, the majority of storage is occupied by such cold videos. So with this approach, we get maximum benefit but with minimal cost. Now, you may ask, some videos do become viral. What in that case, right? We could simply bring back more physical replicas like we had earlier in the default storage layout. The chance of this happening is low, but we can handle those. In summary, semantic replication is a storage growth rate reducing optimization that uses properties of the data instead of just treating them as bits. To achieve this, though, the underlying storage system needs to support a few properties. First of all, we want the physical replicas of the same semantic replica to be present in the same failure domains. Consider this. If we assume that the chunks of videos are spread across different failure domains, then in the off chance of a region going down, we will incur a globally correlated loss. That is, the probability of failure for all videos is the same, and this happens at the same time. This is not desirable. Also, the other property we need from storage systems is that all physical replicas of different semantic replica are present in different failure domains. This guarantees isolation, particularly when in compact storage mode where we need that property. The third thing that we need from a storage system is the ability to modify the number of physical replicas for each semantic replica. This is what actually lets us compact cold videos or increase replication if it becomes viral again. Next, Dan will be walking us through how we went about meeting these requirements from a storage system's perspective and what we learned along the way.
Hello everyone, and Chidu, thanks for giving us an insightful overview of how videos get stored at Facebook. My name is Dan, and I'm a software engineer on Everstore, Facebook's blob storage system. Since we started working from home, I picked up a new hobby, which is weightlifting, as you can see on the background. One of the core principles of gaining strength is progressive overloading. Interestingly enough, a same methodology can be utilized for scaling up services. Today, I will talk to you about our journey of building the semantic replication engine that allows us to achieve the optimizations that Chidu presented. I will start by giving an overview of the solution that we have been utilizing for storing blobs at Facebook, including videos. Then, we will take a look at our initial attempt of doing semantic replication in production with placement policy volumes, which unfortunately did not scale. However, that was a good learning experience as it allowed us to better understand the system and identify the flawed assumptions. In the last section, we will analyze together the latest version of the system and how it is used for doing semantic replication. Let's start by taking a closer look at the classic solution utilized for storing blobs at Facebook. Each blob that gets uploaded to Everstore is stored in a logical volume. This can be visualized as a folder containing a collection of files, For example, we could have volume 1 containing the following list of blobs, A, B, C, all the way up to K. However, this is just a logical mapping. We are a storage team, so we have to focus on storing the bytes on disk. So let's see how we actually do this. In order to represent the bytes on disk, we utilize the concept of physical volumes, which can be visualized as a materialized version of a logical volume. For each logical volume, we maintain two physical volumes that are stored at all times in distinct regions. The reason why I say at all times is that the regions in which the physical volumes reside get updated in order to do data rebalancing across the system. This is a critically important operation as our capacity is on a continuous shift. For example, new data centers will come online. Existing ones might get expanded or shrunk. Old ones might get decommissioned, and so on. This data management model allows us to achieve a highly durable, highly available, and DR-compliant storage system. However, this system does not satisfy any of the requirements that Chidu presented. In our first attempt to solve this, we decided to create a new class of volumes called placement policy volumes. Those would have physical volumes in each region where we have capacity. Well, how can these volumes be used to achieve semantic replication? Well, on the upload path, the pipelines responsible for the video processing would create the different encodings and specify for each of them the list of regions where the data should be stored. Later on, other pipelines responsible for evaluating the hotness of videos would determine the latest called videos and update the list of regions from 2 to 1. This would allow us to run compaction on the storage side and thus reclaim the space. One important aspect to notice is that in this scheme, the application will have full control of the data placement. But that also means that rebalancing data across regions becomes the application's responsibility. This is an important shift of responsibilities that we should keep in mind. So let's analyze together the pros and cons of this approach to understand why we decided to architect another system. One of the main benefits of this solution is its simplicity, which makes it easy to reason about. This also enabled us to move fast and ship it to production in just a few months. Another selling point is the flexibility that it provides. Not only it allows the product to control the replication factor, but also the data placement. However, testing this at Facebook scale actually surfaced a few problems with common root cause. These placement policy volumes introduced high overheads in multiple parts of our system. For example, our background syncing service has experienced regressions on multiple fronts. First of all, the I/O utilized for reading metadata increased more than an order of magnitude. The reason for that is that for every sync that is performed, it is performed against a physical volume. However, you need to get all the metadata from all the physical volumes. So that means that we move from doing 2 metadata reads per sync to doing more than 10 metadata reads per sync. What makes the problem even worse is that in order to do a full syncing round, we actually end up doing more than 100 metadata reads. That means moving from 4 to over 100. Another issue is that performing a full syncing round of all the physical volumes of a placement policy volume has also drastically increased, which could result in lower durability. On the storage node side, we have discovered that in the small regions the memory utilization had gone dangerously high, which would put our availability at risk. The last piece of feedback that we received from the application side was that data rebalancing was not as trivial as anticipated. Having learned all these valuable lessons, we went back to the drawing board and started redesigning the solution. As a result of all the discussions, we decided to introduce a new data grouping concept. A mega volume is a collection of logical volumes that have their physical volumes in the same set of regions. Well, how is this container useful for semantic replication? Let's take a look at an encoding, and let's say that it gets split into 9 chunks. By writing all the chunks that form an encoding to the same mega volume, we can keep them grouped in the same failure domains without being forced to upload all of them to the same logical volume. This is an important aspect as it prevents the unavailability of a single logical volume to impact the write reliability. Moreover, by limiting the size of a mega volume in the petabytes order, it becomes a shard that can be utilized for doing rebalancing across regions for data needing to be collocated. Thus, we have obtained a new shard that keeps data collocated, has the same read and write reliability as the old system, and can be moved around for rebalancing purposes. The next problem that we started exploring was how to prevent encodings belonging to the same video ending up in the same failure domain at any point in time. As computer scientists like to invent new concepts all the time, we decided to introduce another data grouping that was masterfully named semantic volumes. A semantic volume is a tuple of megavolumes that reside in distinct regions at all times. Well, how does this new concept actually help us? Let's take a look at the video and assume that it has 3 encodings. By uploading each encoding to a different megavolume, we will ensure that each encoding will live in a distinct set of regions at all times. That means that we can achieve data rebalancing across all our regions and also keep the encodings in distinct sets of regions. Thus, we have achieved the means for performing semantic replication. Moreover, the new setup is linearly scalable as it relies on the same primitives that we have been utilizing successfully so far, the logical and physical volumes. The novelty of this design is the logical grouping of data and enforcing different constraints on tuples of such groups. On one hand, megavolumes can be seen as enhanced logical volumes that enable collocation of data despite rebalancing. On the other hand, megavolumes can also be viewed as generalized physical volumes for the semantic volume. By using this analogy, one more benefit of this approach is that existing rebalancing algorithms could be reused. As with any system, we must consider and analyze the trade-offs. We have improved on the scalability axis, however, we lost the ability of controlling the data placement at a granular level. But this is an acceptable trade-off, as all the requirements for semantic replications are met. So what lies ahead of us? Well, first we want to increase the adoption of the new engine, which has just been launched to production. Then we want to migrate all the old videos to the new engine, such that we can achieve a one-time saving on the storage side. The next step will be exploring applying semantic replication on other content types. One such example would be photos that get stored in different resolutions. Thank you for your time and attention, and hope you enjoyed our talk at System at Scale.